Hello everyone, I'm Shao-Da Wang from National Tsinghua University in Taiwan. The topic of the presentation is on the performance enhancement of Cantilever Diaphragm Piezoelectric microphone. Here is the outline. I will start from the brief introduction of MEMS microphone about the application and the key parameter of the microphone. And then I will go on with the design concept with the unimorph cantilever microphone. After the fabrication process, I will show the acoustic measurement result of the microphone, and go on with the conclusion. Microphone usually used in human-related sound detection, and in different applications, there are various bandwidth requirements. And also, it can use in live monitoring by whistling detection and failure monitoring by vibration noise detection. The two main sensing mechanisms of a MEMS microphone are capacitive sensing type and piezoelectric sensing type. Capacitive sensing type feature low thermal influence and CMOS monolithic capability. When the sound pressure applied on the diaphragm, the gap between these two electrodes will change and the capacitance will change too. But the narrow sensing gap will suffer from the pull-in effect, and also, it is easily influenced by the dust and the water vapor in the air. And for the piezoelectric sensing type, it usually features simple diaphragm structure. When the sound pressure applied on the diaphragm, the stress induced in piezoelectric material can induce charge by the piezoelectricity. But the higher dielectric loss in piezoelectric material means that the signal-to-noise ratio needs further improvement in this sensing type. So in this study, I try to improve the signal-to-noise ratio by the design of the diaphragm. And go on with the two key parameters of the microphone. First is the signal-to-noise ratio. Signal-to-noise ratio is defined as the difference from signal to self-noise. If we can achieve high signal-to-noise ratio, we can get higher resolution and better sound quality. And for the bandwidth is the region we can get the same response of the input acoustic signal. In this study, I focus on the speech recognition application, so the bandwidth will be designed between 0.5 kHz to 8 kHz. Let's talk more about the bandwidth. The high cutoff frequency usually constrained by the resonant frequency of a diaphragm in MEMS microphone. As an example, if we design the MEMS microphone resonant frequency at 14 kHz, the 3 dB high cutoff frequency will located at 7.6 kHz. It is approximate half of the resonant frequency of the diaphragm. So if we can achieve higher resonant frequency of the diaphragm, we can get much more wider bandwidth. And the low cutoff frequency is usually constrained by the acoustic short circuit effect. In order to improve acoustic short circuit effect, we need to get smaller gap or larger backside cavity. So this study starts from the unimorph cantilever microphone and try to improve the signal-to-noise ratio and bandwidth by PCT and electrode pattern of the unimorph cantilever microphone. And after fabrication, this study proposed an easy way to improve acoustic short circuit effect by applying DC bias on the piezoelectric material to suppress the stress-induced warpage. The analytical solution of unimorph MEMS microphone shows that the signal-to-noise ratio will be determined by this parameter. And I try to combine the bandwidth and diaphragm area in this equation, and we can get a final relation between the signal-to-noise ratio and bandwidth. And they will be influenced by these four parameters: input pressure, piezoelectric properties, electrode placement, and the diaphragm geometry. In this study, we'll try to modify the electrode placement and diaphragm geometry to achieve higher performance of the piezoelectric MEMS microphone. At first, let's look at about electrode placement ratio of the Cantilever microphone. In figure below, as we can see, the electrode placement ratio at 44% will let the microphone achieve highest energy output. So at this time, the tip portion of a diaphragm will have a PZT remain non-use, and it will be an extra mass of the diaphragm. So if you can remove the PZT at this portion, the equivalent mass of the system will be decreased, and the resonant frequency can be improved, and also improve the bandwidth by the mass reduction. So the proposed design modify the PZT and electrode placement at the same time. And also this study proposed two types of reference. First one has the same geometry compared to proposed design, and the second one change the length-width ratio to make the resonant frequency as same as the proposed design. In finite element simulation result, we can see that the proposed design has better bandwidth compared to reference 1 and better signal-to-noise ratio compared to reference 2. And the normalized signal-to-noise ratio multiplied with bandwidth has also 70% increase compared to two types of reference. And go on is the fabrication process. At first, we will take the SOI wafer deposit with a PT downward electrode and a PZT piezoelectric material. First, after PZT wet etching, the contact pad of a downward electrode can be opened. And then, by the lift-off process, we can define the top electrode. After two-step frontside etching, we can define the PZT pattern and the gap between diaphragm. And after two-step backside etching, we can suspend the structure and complete the process. The fabrication result can be observed by SEM micrograph. The proposed design and two types of reference has been successfully fabricated. And the boundary of the electrode has been also measured by the focused ion beam. The center of the diaphragm has been also observed by SEM. The gap between the diaphragm is 5 micrometer and 1 micrometer. The profile measurement result shows that after remove the PZT and electrode at the tip portion of a proposed design, the residual stress-induced warpage has been improved by the stress source remove. Device will be bonded on the design PCB and capped with a metal cap to form the back chamber of a MEMS microphone. And the acoustic measurement will be set up in the anodic box with a reference microphone. The picture of the anodic box shows that the device under test and reference microphone will be placed 50 cm away from the speaker. After going through the amplifier circuit, we can detect the final voltage output. And also we can apply DC bias on the piezoelectric microphone to suppress the stress-induced warpage. The signal-to-noise ratio measurement result shows that the proposed design has 4.5 dB increase of signal-to-noise ratio compared to reference type 2. And the frequency response measurement result shows that the proposed design has nearly 2 times larger high cutoff frequency compared to reference type 1. And let's talk about the DC bias effect. When the DC bias applies on the piezoelectric material, the inverse piezoelectric effect will cause the diaphragm bends down by the deformation. So the tip displacement will reduce from 44 micrometer to 31 micrometer after 15 volt bias apply. And also the piezoelectric coefficient has been increased after apply 10 volt bias voltage. So let's look about the frequency response after DC bias for the proposed design. The low cutoff frequency of proposed design reduced from 1.4 kHz to 0.9 kHz. And also the signal to noise ratio has 3 dB increase at same time. So in conclusion, the proposed design increased bandwidth compared to reference 1 and increased the signal to noise ratio compared to reference 2. And the multiplication of these two has also been increased by 70%, just like the simulation. And if we apply the DC bias on the diaphragm, we can further improve the performance of the proposed design and other design by the warpage reduction. At the end, I want to appreciate the Ministry of Science and Technology in Taiwan for sponsor, and the Coretronic MENS, Taiwan Semiconductor Research Institute, and National Tsinghua University for provide fabrication facilities. Thank you for your attention.